linking doesn't mean anything bad. Okay, so I will briefly recall where we are. First, maybe I recall first. So we were talking about algebraic novelty, so I have introduced the fine algebraic set. So these were the zero sets of some sets of polynomials. So S is a set of polynomials in n variables with coefficients of n, k, and the zero set of S is just the set of all points in an, which remember is just k to the n, such that f of t is equal to 0 for all f in S. So where f of p just means we put the coordinates of the point p instead of the variables and we get the number. So that is so sets of this form are called affine algebraic sets. Then we had introduced, so we had seen that every affine algebraic set is a zero set of an ideal, because the zero set of a set of polynomials is the same as the zero set of the ideal generated by this. And so therefore we can restrict our attention here to ideals. And then we had introduced the Zariski topology. So this was a topology on AN whose closed subsets are the affine algebraic sets. So we have seen that the affine algebraic sets fulfill the axioms of the closed sets of the topology. We call this the Zariski topology, and if X in AN is a subset, we give it the induced topology. Okay. And we had also talked about the idea of an algebraic set, which will concern us a bit more later. So this was just if X, say, is an affine algebraic set, then the ideal of X consists of all polynomials. So we assume that X is in AN, obviously, that the variables match, which vanish on X. So I could just say F restricted to X is equal to 0. So that means F of t is equal to 0 for all P in X. So this is somehow an idea which is kind of canonically associated to X. And one thing which I really did not say, but which I will use a few times, is the statement that if I take the zero set of the ideal, no, which one did I want? Yeah, if I take the zero set of the ideal of X, this will be equal to X, if X is an affine algebraic set. If X is just any subset, you can easily check as an exercise that the zero set of the ideal of X is the closure of X in the Zariski topology. Anyway, so I hadn't done this, so just let me say it. So obviously, the zero set of the ideal of X contains X, because all the elements in the ideal of X vanish on X. And the zero set consists of all points where all of them vanish. So this by definition. So by definition. On the other hand, X is an affine algebraic set. So we can write X is equal to the zero set of J for J an ideal. In Kx1 for Xn. And but you know, what does it mean that it's in Z of? In particular, every element in J has the property that it vanishes on X. So that means, by definition, J is contained in the idea of X. No, that's what this says. But then we know that for the zero sets it will be the other way around. So it follows, thus it follows that the zero set of J contains the zero set of the ideal of X. But this is X. And so we have both inclusions. And then finally, we talked about the Hilbert basis theorem. I mean, we started to talk about the Hilbert basis theorem. For the moment, we talked about Noetherianity. So we had said, so a ring R, which for us a ring is always a commutative ring with 1, is Noetherian if the following two equivalent conditions hold. First, every ideal in R is finitely generated. So I can write it as ideal generated by finitely many elements. And the second statement is that every ascending chain of ideals becomes stationary. So infinite chain of ideals becomes stationary. That means from a certain point onwards, all the ideals are the same. Okay, so you cannot have an infinitely growing chain of ideals. Okay, so this is where we were, and now we want to show that Kx1 to Xn is Noetherian. So I will do something slightly more general because it's easier. So the Hilbert basis theorem says the following: let R be a Noetherian ring. Then, if I take polynomials R x1 to xn, the coefficients in R is also Noetherian. Okay, so what we are really interested in is the case that R is just the field K. So as corollary, we have that our field Kx1 to xn is Noetherian. This is because K is a field. So we know the only ideals in a field are the zero ideal and the whole of the field. And we have remembered this hopefully from the last semester. Are 0 and K. So obviously, I mean, both of them are finally generated. One is generated by 0, one by 1, or also you cannot really have very long chains between two elements. So therefore, K is unitary. And so therefore, the theorem applies and gives me that K is 1 to xn is unitary. And it also follows that the thing that I said, that every affine algebraic set is the zero set of finitely many polynomials. So say x in an is the zero set of finitely many polynomials. So the common zero set of finitely many, namely the point is just if x is equal to the zero set of some ideal, as we had seen before. Now this ideal is finally generated by generator. We know that the zero set of an ideal is equal to the zero set of the set, any set which generates it. So this is equal, so that x is equal to the zero set of f1. No? So here these are, let's just say there exist, no, these are the generators of I, so I just say it briefly. So x is the zero set of some ideal. This ideal is finally generated, so I call the generators f1 to fr. Then x is the zero set of the polynomials f1 to fr. Okay, so now let's prove this Hilbert-based theorem. So, first, so we know by our definition, we have that, so by definition, R x1 to xn is just equal to R x1 to xn minus 1 and then xn. So the polynomials in x1 to xn are just the polynomials in xn whose coefficients are polynomials in x1 to xn minus 1. So this allows us to do induction. So just by replacing, we just have to, we can make induction over n. So we can just take, for instance, to look at this thing, we can just take it as our new r x1 to xn minus 1. By induction, this is Noetherian, and so we use this as Noetherian. So what I mean is, it's enough to show. So by induction, I will say it again afterwards. Induction enough to show if R is unitarian, then Rx is unitarian. Because we know our original R is unitarian, and so this allows me to go from Rx to Rx, from R to Rx1 to Rx1, X2, and so on until Rx1. So this is also the reason why we want to generalize here. This makes it easier to prove it with this R instead of with K, because like this we can make induction over N. For Kx1 to Xn we wouldn't know how to do induction. Okay? So we have simplified by generalizing it, and so we want to show this. So now we make an indirect argument. So we assume Rx is not unitarian. And we will want to show that R is not unitarian. So this is so this is a rather old theorem, Hilbert. It's a reasonably famous theorem, but this proof is deceptively short somehow. But it's still non-trivial. One thing is to So I mean, it looks we'll see in a moment. So how do we do this? So our problem is we have here, say, so this is not unitarian. So let's say let I in Rx be an ideal which is not finitely generated. So we will have to prove something which contradicts the fact that R is unitarian. So either we have to find an ideal here which is not finitely generated, or we have to find a chain of ideals in this thing which does not become stationary. We will do the second. So we have to find a chain of ideals in R which does not become stationary. And you see what our problem is. We somehow have to come from this ideal in Rx to R. So we somehow have to, associate, so relate the problem in this polynomial ring to the problem in R. And so this we do by looking at the leading coefficients of the elements in R. Okay, this is somehow the trick. So look. At leading coefficients of elements in R. So let me carry this out. So we first start. So let f, say 1 in I without 0, a polynomial. So it's a non-zero polynomial, and you want to take it of the smallest possible degree. Of minimal degree. Note we are here, we are now here in Rx, so there's only one variable in X. Okay, we take this element. Now we go on. So we know that the ideal is not finally generated, so we can always choose one more element. We never have the whole ideal. So let F2 be an element in I without the ideal generated by F1. Again, the polynomial of minimal degree. So maybe we record and we say that N1 is the degree of F1 and N2 is the degree of F2, and we can proceed inductively. So for all n, let Fn say plus 1 be a polynomial of minimal degree in I without the ideal generated by the first n element. And we can do this ad infinitum because I is not finitely generated. And again, maybe I shouldn't have called it n, we'll call this L because I don't like the n here. And we call NL plus 1 equal to the degree of Fl plus 1. Okay, so we have this infinite chain, we know these ideas, and we also want to look at the leading terms. So for all I, let AI in R be the coefficient of x to the ni in Fi. So the highest degree coefficient that Fi has. So then clearly we have a chain of ideals A1 contained in A1, A2, A1, A2, A3, and so on, is a chain of ideals. So we want to show that this chain of ideals violates the Noetherianity of R. So we have to show that this chain does not become stationary. It's not that after a certain point all of them are equal. So this does not become stationary. So assume it does, so we make an indirect argument, so assume it does. So then in particular, there will be a point when one is equal to the next. So then exists an L such that A1 to AL is equal to A1 to AL plus 1. Yeah? We want to see that this cannot happen. So then we have that if this is the same, we have in particular that AL plus 1 is in the ideal generated by A1 to AL. So that is, we can write AL plus 1 as a linear combination of these. We can write L plus 1 is equal to sum I equals 1 to L AI BI, where BI are some polynomials. Now we were in Rx in R. We were in R. BI were in R. Okay, so we have that. So let's see. Now I claim this cannot happen. So let's write down an element. Let's say we put G equal to FL plus 1 minus the sum I equals 1. L BI There's one thing I forgot to say, which is very important. And this is actually a bit annoying, but anyway, let me stress it now. So we have talked about these degrees here. So we have that, as I said, NL is equal to the degree. So, it's should have stressed it. Let me stress it now again. So we have FL. So for all L. So, but in particular FL plus Fi plus 1 is inductively an element in I minus the ideal generated by F1 to Fi of minimal degree. And this minimal degree is what's called Ni. Ni plus 1. So thus it follows. So I take the polynomial with the smallest degree, first for the whole of I, then for I minus this thing, so this is a smaller set, so the smallest degree can only get larger. Then I add one more element, I take the element with the smallest degree, so the smallest degree can only get larger because I have less elements to choose from. So thus it follows that N1 is smaller equal N2 is smaller equal, and so on. So always 3. So they are increasing. Okay, so this plays a role here. So I write here times x to the nl plus 1 minus ni. So you see this is a positive power. So this is actually a polynomial. This makes sense. Times fi. So this is an element in. Okay. So we put this. So we first see that G is an element in I minus F1 until FL. Because if not, we can bring it on the other side. So we bring this over. So if this, I can, subtract this whole thing. This. So otherwise, we have that FL plus 1, which is equal to G plus the sum I equals 1 to L Di x and L plus 1 minus Ni Fi, that this lies in F1 to FL, because these are elements in the ideal generated by F1 to FL. I take some linear combinations of them, so this whole sum lies in this ideal, and then if G also lies in this, if G also would lie in F1 to FL, then we would have that the whole, also this element lies there, but we have chosen this not to lie in the ideal generated by the previous one. So we know that this does not lie, that this lies in the ideal minus this. On the other hand, we can compute its degree. So each, if we look at the definition here, each summand so on the right hand side of star has degree nl plus 1, because this one has degree nl plus 1, and here this has degree ni, but I multiply it by, so it's either 0 or it has degree n plus 1, but we multiply it by this, which makes the degree also an n plus 1. So all of them have this degree. But what is, okay, so thus it follows the degree of G is at most an n plus 1. But we can now, let's compute the coefficient of x to the n plus 1. Is what? So here the coefficient of x to the n plus 1 by definition is AL. What? L plus 1, yes, certainly. And here, we have here the coefficient is AI. Then if we multiply by this, so we have, this would be in degree the thing of x to the I, but if you multiply by this, the coefficient of x to the I here becomes the coefficient of x to the L plus 1 here. And what is the coefficient? It's AI, the coefficient here, times BI. Which is precise, and we have, by our condition here, that the ideal did not become larger, we precisely have that this element, this is equal to this, so this difference is 0. So thus it follows that the degree of LF plus 1 is smaller than NL plus 1. And this is a contradiction to our choice, because we have chosen the degree of G is smaller than this. And this is, however, a contradiction to our choice, because we have chosen Fl plus 1 as an element with minimal degree in this. It's a contradiction to our choice of Fl plus 1 to be of minimal degree. In this thing. Okay, so this contradiction shows that everything he said here was wrong, and we have to conclude that our assumption here was false, namely the chain became stationary, and thus R is not Newtonian. Okay, so that's the proof. Okay, so now we will want to, this fact that every affine algebraic set is a zero set of finite many polynomials is some kind of comfort, so that we don't worry about having this infinite thing, but by itself maybe we don't care so much. But this fact that kx1 to xn is Noetherian actually has also geometric consequences, and one of them is this about irreducible components. So I will want to explain this. So I already alluded to this at the very beginning of the first lecture. We know that if we take the zero set of the polynomial x times y, say in A2, so I call the coordinates here x and y instead of x1 and x2, this obviously is equal to the zero set of x union the zero set of y, that you know. You can easily see that obviously none of these two is equal to the other sum, but it's not true. But x is different from v of xy, and v of y is different from v of x. So we have been able to decompose this thing into this algebraic set into smaller algebraic sets. So if this is not possible, we will call the algebraic set irreducible. So if we cannot decompose an affine algebraic set into two smaller affine algebraic sets, then it's irreducible. So that means an affine algebraic set is irreducible if whenever I write it as a union of two affine algebraic sets, one of them must be equal to it. Okay, so that's a kind of crazy thing, but that's the way it is. And so the claim will be that every affine algebraic set can be decomposed into finitely many such pieces, which are irreducible in this sense. Okay. So now, we will want this whole thing that I just say to be. So maybe I can just say it. So to show every affine algebraic set can be written as union of finitely many irreducible affine algebraic sets namely, as I said, such that whenever I write any of them as a union of two affine algebraic sets, it must be equal to one of the two. Now, in order to be able, now we talk about affine algebraic sets and affine varieties. Later we'll talk about projective situation. We also want to talk about quasi-projective varieties. So we want to make things work in more generality. So we formulate it a bit more abstractly so that it will apply to all future situations. And this we do by using, by formulating it topologically. So, in order to, for our result, to be applicable in all situations in the future, and we will formulation topologically. So as a statement, in this case about the Zariski topology. So that means if you find it easier, whenever I say, you can read, so closed set would then, can then, if you wish, read it as a affine algebraic set. So the argument, is precisely the same, but we do it with this Zariski topology, and so I have to state what I want in terms of that. So first, I want to say what it means to be irreducible for the topological space. What? Oh no, we didn't. Okay. Where am I? Yeah. Okay. So this is definition. So a topological space is called irreducible if the following hold. Want to say it like this? Yeah, okay. So X. So if whenever you can write X equal to X1 union X2 for X1 and X2 closed subsets, we get, it follows, we have x is equal to x1 or x is equal to x2. Okay. X is called reducible if and only if it's not irreducible. So if you want, you can also say this directly. So that means you can write x is equal to x1 union x2 with both x1 and x2 proper subsets. Okay, so as I said, the case we're actually interested in is in a fine algebraic set with a Zariski topology. So in a fine algebraic set is irreducible if whenever I can write it as a union of two affine algebraic sets, it must be equal to 1. Just a few. So I should maybe say, so we are dealing, we are always thinking of the Zariski topology when we are introducing these concepts. So in the kind of normal life, this context, this concept makes very little sense. If you take, I think if you take a Hausdorff space, you can most likely prove that the only irreducible subsets are points or something like that. So it's a very stupid concept. But for our Zariski topology, which is sufficiently terrible, this is a reasonable notion. And then, so I just want to say something useful. So if X is an irreducible topological space, then every non-empty open subset is dense. And U subset X non-empty and open, and it follows that U, so the closure of U is equal to X, so U is dense in X. And if you wish, you can also see as an exercise, I will not say it, that U is also irreducible. Obviously with the induced support. Just to make it clear, we say that a fine algebraic set is irreducible if it's irreducible as a topological space with a Zariski topology. So, for instance, as an example, we have seen a point P in AN is irreducible. Okay, that seems obvious. And you cannot write a point as a union of two things. If you take just this example, the xy subset A2 is reducible. No, because it's so, okay. Now we will want to show that every affine algebraic set is a finite union of irreducible affine algebraic sets. And we want to formulate this topologically, so we have to state a property that the Zariski topology of affine algebraic sets has, which will imply this. And this property has to do with the fact that kx1 to xn is Noetherian, and so we call this property that the topological space is Noetherian. So let me state this. Definition. The topological space say X is called unitarian if it has a very similar, and so say a descending chain property of for closed subsets. So if every descending chain of closed subs, so X, so again an infinite chain, of closed subsets becomes stationary. So that means there exists an n such that xn is equal to xn plus 1. Okay, from a certain point onwards, if we have closed subsets of X which become smaller and smaller, this cannot happen infinitely many times. After finitely many steps, they must be all the same. So you cannot infinitely many times take away something from a closed subset. Obviously, this is something, like if you take the real numbers with the standard topology, that's certainly not unitarian. But we now want to see that, now we have to see that the Göttsche topology is unitarian. So let me state this. Remark. First, any subspace, so that means you have a subset with the induced topology, Y of a unitarian topological space is unitarian. The second statement is that AN with the Zariski topology is unitarian, and then it follows by one. It follows from this that every affine algebraic set with the Zariski topology is unitarian. Because we have the affine algebraic sets are also given the Zariski topology, which is just the induced topology from AN. So if AN is unitarian, then by part 1 also every subspace of AN is unitarian, in particular every affine algebraic set is unitarian. Okay, so let's prove it. So let's say we want to take a descending chain in Y. So let Y by 1 by 2, a descending chain of closed subsets. In Y. So now we have to use that Y carries, so we use this original topological space called X. We use that it carries the induced topology. So the closed subsets of Y are the intersections of Y with the closed subsets of X. So we can write Yi equal to Y intersected Xi, where Xi is closed in X. Okay, so now the obvious idea would be then the xi form a descending chain and this becomes stationary. That doesn't quite work because the way we have set it here is not automatic that the xi are one contained in each other, but we can easily arrange that. So we replace xi by the intersection over all j smaller equal to I xj. So maybe I call this xi prime. So now this thing, xi prime, you can see this has the same intersection with y as xi, because the intersections are contained in each other. So then yi is equal to y intersected xi prime for all I. And these form a chain. Chain of closed subsets. So it becomes stationary. So from a certain point onwards, they are all the same. Exists in N such that xn prime is equal to xn plus 1 prime, and so on. So thus, obviously, because yi is just y intersected with that, we also have yn is equal to yn plus 1. So the chain becomes stationary. So this is the first statement. So it follows quite directly from the fact that we have the subspace topology. Now the second statement, which is obviously what I mean, if you look at it, now I unfortunately wiped it out, but the somehow the Noetherian condition says we have a descending chain of closed subsets and become stationary. The Noetherian condition for the corresponding kx1 to xn goes in the opposite direction for ideas. But it's kind of clear that the bigger the idea becomes, the smaller the zero set. So these precisely correspond, and therefore these two Noetherian conditions are somehow the same. So let's see. So 2. Let x1, so an x1 is to be a descending condition, descending chain of closed subsets of an. Then I can look at the corresponding ideas. So then I of x1 contained in I of x2 and so on is an ascending chain. In kx1 to xn. No, because when the set is smaller, it imposes less conditions on polynomials to vanish there. So a descending chain of closed subsets gives us an ascending chain of ideas. So this ascending chain becomes stationary. So this, because kx1 to xn is Noetherian, this becomes stationary. So that means that, so there exists again an n such that I of xn is equal to I xn plus 1 and so on. But now I've just shown you that for a closed subset of an, the zero set of the ideal of the closed subset is the closed subset. So, but we know that the idea of the zero set of the idea of all each xi is just xi. So thus we have xn is equal to xn plus 1. So the chain of the closed subsets became, the descending chain has become stationary. And this shows that this is a Noetherian topological space. And you can also see that basically the fact that an and any fine algebraic set is Noetherian is a direct translation of the Noetherianity of the polynomial. So this is therefore the thing that this is what we use to draw the consequences from the Noetherianity of kx complex A. So now, therefore, I can now state the story, the theorem about irreducible components as a consequence of this. So, theorem, also irreducible definition. Every Noetherian topological space say X is in a unique way a priori a finite union X equal X1 union XR of irreducible closed subsets subject, so to make it unique I have to impose a condition such that none of them is contained. So xi is not contained in xj for I different from j. Obviously, you could always add as closed subsets any point in any of them, so that it's not unique. So, but if I impose this condition that I don't add another random element which is contained in one which I had before, then it's a unique way finite union of irreducible closed subsets. And these things, the xi, are called irreducible components of X. So maybe I can stress it again. So if we just talk about affine algebraic sets, you can directly say it in these words. So every affine algebraic set is up to ordering in a unique way a finite union of irreducible affine algebraic sets if I impose the condition that none of them is contained one in the other. Okay, so it's just the same statement. Okay, so this is, yeah, we shall see. This is, will be, so we have two parts, existence and uniqueness. Uniqueness is relatively easy, we'll see. Existence is a very indirect argument, so it gives you no clue at all how you find it. So it's, I just assume I cannot do it, and then it leads to disaster, but it doesn't, so that's a little bit unsatisfactory. And in fact, if you're given an affine algebraic set, meaning in terms of equations, it might not be so easy to find its irreducible components. There's not a particularly nice way of finding that. I mean, obviously, if you make a drawing, you can, in the picture that I showed you, you can see it, but it's not quite as trivial. And so anyway, the proof will give us no insight into that. So first we show the existence. So I claim it's enough to prove the decomposition X equal to X1 union XR into irreducible closed subsets. So once I have such a decomposition into irreducible closed subsets, this condition here is trivial to achieve. Whenever one of these things is contained in another one, I throw it away. Then the union of them will still be the whole thing, because after all, the one I've thrown away was contained in another, so the union doesn't change. So the condition xi is not contained in xj for I different from j is then achieved by throwing away, or getting rid of whatever, throwing away any xi contained in an I. Okay? We only have to show we can decompose it in this way, that we can do it in this kind of minimal way is trivial. We just throw away whatever is there too much. Okay. And now we make an indirect argument, so we assume we can't do it. Assume X does not have such decompositions. Into finitely enclosed, finitely many irreducible closed subsets. Okay. So if that is the case, it cannot be that X is irreducible, because if X was irreducible, we would have decomposition. The decomposition X is equal to X. So thus X is reducible. So thus we can write X as a union of two smaller closed subsets. Where X1 and X2 in X are closed, and none of them is equal to X. Maybe I don't want, I wanted to give a notation, this is Y. So furthermore, so if both X1 and Y1 could be decomposed into finitely many irreducible closed subsets, then I could just take the union of all the subsets from here, and I get the decomposition of X. So therefore, if X doesn't have such a finite decomposition, either X1 or Y1 does not have a decomposition into irreducible closed subsets. Into finitely many. One of the two. Obviously, as I chose a name at random, I can call it X1. Does not have a decomposition. into finitely many. Irreducible closed subset. But now, think of it. We have started, so, and obviously we have started with X not having a decomposition into finitely many irreducible closed subsets. Now we found that this was the only assumption we made. And now we found that another set, X1, which doesn't have a finite, a smaller set, X1, which doesn't have a decomposition into irreducible closed subsets. So X1 has precisely the same property as X, so we can repeat the argument. So X1 satisfies the same properties as X, so thus we have, there is X2 in X1 which does not have a decomposition into finitely many irreducible closed subsets. We can continue this argument with X2, which has again the same property. So inductively, we get a chain of those subsets. So thus inductively, we get a chain X. So strictly contained in X1, because as you can see, we have seen that here none of the two is equal to X, and here, by the same condition, X2 is not equal to X1. It's always, because this thing is reducible at each step, so the two pieces are actually smaller, so we get a chain like this. An infinite chain so we have an infinite chain which is constructed in such a way that at each step the things actually do become smaller, so which does not terminate. And this contradicts the fact that X was Noetheric. But as you can see, this is, this tells you precisely nothing about how you get the irreducible components, but at least proves that you have to have that. Okay? This is, extremely indirect argument. Okay, now we come to the other direction. Not the other direction, the uniqueness. Here we just have to look at the defining properties. So, have it here, yeah. No, I don't have it here. So, assume we have two such compositions, that X equal to X1 union XR, and also equal to Y1 union YS, two decompositions into irreducible closed subsets with the properties enough above, so two decompositions into irreducible closed subsets with the property that we had also here, so that Xj is not contained in Xi, and also Yj is not contained in yi for I different from j. And we have to show that, what do we have to show? We have to show that R is equal to S and that there is that each xi is equal to 1 yj and vice versa. No, up to ordering they are the same. So we can write obviously xi, we take any I xi, we can write this as the union over all j, from 1 to s, and xi intersected with yj, because the union of the yj's is equal to x. So this is fine. So the yj's are closed subsets of x. So therefore, xi intersected yj is also closed. So the xi intersected yj are closed in xi, and xi is irreducible. So thus, one of these intersections must be equal to xi. No? We have written xi as a union of closed subsets, so it must be equal to one of them. We have written a union of finitely closed subsets, so it must be equal to one of them. So thus, there exists a j with xi is equal to xi intersected yj. But what does it mean? Xi doesn't get smaller when we intersect it with yj, so that means xi is contained in yj. Now, we can also obviously argue the other way around with yj. So if we write now yj as a union from I, let's say k equals 1 to whatever the number r, yj intersected xk, then the same argument will show there exists a k. So by same argument, there exists a k such that yj is contained in xk. No, it's just the same argument, no, with the role of the I with the x and y interchange. So thus we have that. So thus it follows that xi is contained in yj is contained in xk. But now remember, we made this condition that none of these xi's is contained in the other unless obviously I and j are equal, then they are the same. So it follows, so by the condition xi not contained in xj for I different from j, we get that I is equal to k. So in particular, obviously, this one is equal to this, and this one being squeezed in the middle is also equal. So that's xi is equal to yj. So each xi is equal to one of the yj's. And in the same way, also each yj is equal to one of the xi's. So it follows that the number of things here is the same, and they are just permutations of each other. And thus, R is equal to S, and x1 to xs is the reordering of y1. Well, it was actually R, anyway, by R is equal to S, but still. Okay, so this is the proof. Okay, so this was maybe not so difficult, one just carefully uses the property of irreducibility. But the first proof is rather, well, it's not difficult, but it's somehow not very illuminating. So later we will concentrate mostly on studying irreducible algebraic sets, so they are easier to deal with, and as every algebraic set is a finite union of irreducible algebraic sets, you can say that if you understand irreducible algebraic sets, you understand all algebraic sets, because you understand all the pieces. And so I will give a name to irreducible algebraic sets. I call them algebraic varieties. So definition and define variety is an irreducible affine algebraic set. Actually, sometime later we will change this definition. We will say what it means, what a more general notion of variety is, and then we will say what it means for two varieties to be isomorphic, which means for all means and purposes the same, and then an affine variety will be a variety which is isomorphic to an irreducible affine algebraic set. But for now we take this definition. So now we can, so I promised you that the ideal of an affine algebraic set would somehow reflect in its algebraic properties the geometric properties of the affine algebraic set. So we can see one instance here. So there is an algebraic criterion for an affine algebraic set to be irreducible. Namely, this is the following statement, proposition, so that X in the N be an affine algebraic set. So X is irreducible if and only if, the idea of X, so it's of course an idea with X1 and is a prime idea. Okay, so this is the property. And actually, there will be some reason why we like very much that this ideal is a prime ideal. We'll see that later, and so that's also the main reason why we kind of restrict our attention to irreducible algebraic sets most of the time. So let's prove that. So I expect to remember what needs to be a prime ideal. So that means if we have a product of two elements in kx1 to xn which lies in Ix, then one of the two factors must lie in Ix. And I hope you remember that, but if you don't, now you heard it again. So assume that X be irreducible. And we take two elements, f and g, don't know what I wrote here. So we take two elements f and g in Kx, such that f times g are elements in Ix, f times g is an element in Ix. So then obviously x, so if f times g lies in Ix, so that means f times g is 0 on x, so it's 0 at all points of x, that means x is contained in the 0 set of f times g, which is the 0 set of f union the 0 set of g. So therefore we can write x as x intersected the 0 set of f union x intersected the 0 set of g. This is a decomposition of x into closed subsets. No, the 0 set of f and 0 set of g are closed. So it's a decomposition into closed subsets. So by the fact that x is irreducible, x must be equal to one of them. X is equal to x intersected zf, or x is equal to x intersected zg. But that x equal to x intersected the 0 set of f just means that f vanishes on x, so that f is in the idea of x. So this is the same f in ex, or f or g. Okay, so that was quite. So we apply the reducibility to the product of these two elements, and we see this implies that if the product lies in the ideal, then one of the factors must. Now the other direction is about as simple. We do it by contraposition, so we assume that x is not irreducible. And we have to show that we are not dealing with the prime. So assume x is equal to x1 union x2 for closed subsets. x1, x2, which are both strictly contained in x. So none of them. No, so in particular, so this saying that x is reducible. So now I can look at the 0 set of I of x1. I mean, this was x1 is a closed set, so the 0 set of this ideal is it itself. This is strictly contained in x, because that's what we said. So therefore, there must be, so this 0 set is strictly smaller than x, so there must be an element in the ideal of x1 which does not vanish on the whole of x. So that is, it follows, there exists an f1 in the ideal of x1 without the ideal of x. And obviously we can argue the same way with x2 instead of x1. So in the same way, there exists an f2 in the ideal of x2 minus the ideal of x. Okay? But if what happens if I take f1 times f2? So F1 vanishes on x1, F2 vanishes on x2, so the product vanishes on the union. So the product is the ideal of x. So we have found two elements which none of them lies in the ideal of x, such that their product lies in the ideal of x. So this so that means that Ix is not prime. Okay. So you see, I don't think there's. I mean, my time is almost up. I cannot really start something new now. So maybe I will stop. Next, I will talk about the Hilbert-Nullstellensatz, which tells precisely about the relation between the ideal of an algebraic set and the corresponding zero set. But okay, that we'll do next time. Okay, thank you. So I